I want to move on and start talking about 2D NMR spectroscopy. And what we're going to do, we'll be using this as a tool, very, very useful for structure solving. There's a whole sort of alphabet soup of different techniques, but rather than just unleashing a torrent, I mean, people do research in this area just like they do research in organic chemistry. And so the big thing is invent a new technique to solve specialized problems. But rather than trying to sort of talk broadly about everything, we're going to focus on getting a few tools in our toolbox and see how to use these techniques to address different problems. We'll start out with two tools in the toolbox. That will be HMQC and Cosi techniques. And then we'll add some more tools, and I'll try to put them into some sort of context. There are two additional lectures that aren't specifically on 2D that will come in either possibly next time or the time after that. So we'll be talking specifically about the nuclear Overhauser effect, which applies to 1D NMR as well. And we'll be talking about dynamic NMR and dynamic effects in NMR spectroscopy. But we're going to start, so our next homework set will start to bring in 2D, and I'd like to get you familiar with the tools. All right, theory, I'm going to start really, really simple-minded. And I think this is actually a good way to think about things. So in 1D, we said the basic idea was you pulse, and then you observe, right? That's your 90-degree pulse. The observe is your FID. Have you now seen your FID on the spectrometers? Have you seen this? You know, the little wiggly, squiggly cosine wave with a die-off. So this is your FID. And of course, what you've got here is an amplitude domain. And then over here, you have time, right? This is literally your signal dying off with time and the cosine wave that corresponds to the periodicity of the various nuclei. And so the whole idea in a 1D Fourier transform is this time domain on the x-axis ends up getting transformed to a frequency domain, and that's your parts per million. And so your spectrum still has amplitude on the vertical axis, and it has frequency in the units of ppm on the horizontal dimension. And the reason we call this one-dimensional NMR spectroscopy is not because this is a 1D graph. It's not. You'd say this is a 2D graph. It's because you have one time dimension, and that gets transformed to a frequency dimension. Now, in 2D NMR, you get two time dimensions in the FID, and they get transformed into two frequency domains. So I'm going to give you, just as I have given you my simplified version of an NMR spectrometer, an IR spectrophotometer, and a mass spectrometer, and so forth, I'll give you my simplified version of a 2D pulse sequence. A 2D pulse sequence is going to be pulse, wait, pulse, observe. And so what you do when you do this is you get two time dimensions, because the wait is you're waiting for some time. You're going to vary the wait, and then you observe. And so this first wait becomes time 1. We'll call that T1. And the second wait becomes T2. Now, these are not to be confused with the capital T's we talked about for relaxation. Remember, we talked about capital T1 is vertical, is spin relaxation, where the magnetization returns to the z-axis. And capital T2 is spin lattice relaxation, where the magnetization spreads out in the xy plane. These are lowercase t's. And they, in turn, transform when you do a 2D FT. They transform to two frequency domains. And so you get a spectrum that might look like this, where you have one domain here, and this is called your F2 domain, and then another domain here, and that's called your F1 domain. Now, what does this mean? As you're varying well, you understand here, of course, in T2, you're collecting a signal, and it's dying off with time. So you understand that basic transform, that if the periodicity of this signal is 1 cycle per second, we get a line at 1 hertz. And if the periodicity of this line is 2 cycles per second, you get a line at 2 hertz. And if it's a composite of 1 cycle per second and 2 cycles per second and others, you get a spectrum consisting of many lines. Now, similarly, as you vary this T1, let's say starting with hypothetically a millisecond in the first experiment, then the next experiment 2 milliseconds, the next experiment 3 milliseconds, the next 4, another periodicity occurs. In other words, your FID, what you observe in this time, also shows variation that occurs in time. Variation in amplitude, a periodic variation. Those variations transform to the second frequency domain. And so you get a spectrum now that consists of 2 frequency domains. It is, of course, plotted 2-dimensionally, but it is really, just as this is actually a 2D graph, this is a 3D graph, if you will. And typically these days, the way we express it is as a topological map. So you'll typically see a series of contours. That's just like if you've ever seen a topographical map of the mountains, each contour represents a certain height. So a very tall peak has many contours, and a short peak has fewer contours. So it's 3 dimensions being represented, being projected in 2. But again, the reason we call this 2D NMR is not because there are 2 dimensions in the graph, but rather because there are 2 time dimensions. All right, that's what I want to say about sort of the basic mechanics of the experiment. There are 2 general types of 2D NMR experiments. One of these experiments is one of these families, the one that we'll be talking mostly about, is correlation experiments. Correlation means connectivity. It means literally what's connected to what. Another way of thinking of this is coupling. It can be proton-proton coupling. It can be proton-carbon coupling. That's what correlation experiments give you information on. You've already been using this type of information from coupling patterns and coupling constants. When you see a triplet here, you say, oh, that's a methyl group, and it integrates to 3 hydrogens. You say, oh, that's a methyl group that's next to a CH2 group. When you see a quartet here, and it integrates to, to 2 hydrogens, you say, oh, that's a methylene group that's next to 3 hydrogens. Maybe it's next to a methyl group. And correlations give that same type of information. When you see a 17 hertz coupling in a transalkene, you say, oh, that 17 hertz coupling must have a partner somewhere. Ah, here is its partner that also has a 17 hertz coupling. So you're already using connectivity information in helping to deduce your structures. 2D experiments provide that information in a more general term. The other type of 2D experiment that we'll be talking about are Overhauser effect experiments. We'll be talking more about the nuclear Overhauser effect in a couple of lectures. Those give rise to information on spatial proximity. These can be very useful for information about stereochemistry and conformation. All right, my philosophy on teaching 2D NMR spectroscopy, as I said before, there's a whole alphabet soup of techniques out there. My philosophy is not to bombard us, but to give us a small box, a small toolbox of what I'll call core techniques. In other words, techniques that if we are good at, we can use to solve a variety of problems. And then if you're good with those techniques, you'll be able to say, oh, here's a hole in my tools where I have a very specialized problem that isn't being solved by these tools. And you can go to Phil or go to the NMR manual and say, oh, I'm encountering this particular problem with a Cosi, and a Toxie isn't helping me out, but I remember him saying something that there was some type of technique called a relay Cosi, and saying I can add that to my toolbox. So, okay, the first two tools that we'll be talking about are Cosi, which was really the first main 2D technique. It stands for correlation spectroscopy. And so this is typically proton-proton, or let's just say homonuclear coupling. And then the second technique that we're going to add to the toolbox is HMQC. And this is heteronuclear correlation. Well, all right, I should say something. So we're learning about the modern versions of the experiments. HMQC uses something that's called inverse detection. That means on the F2 dimension, you're detecting proton, and on the F1 dimension, you're detecting carbon. The older, less sophisticated version of this experiment was called HetCore. I'm going to put it in parenthesis, but that's not really, it's not the same thing. HetCore was heteronuclear correlation spectroscopy, and now that's what you'd call, that's what you would call HMQC. HetCore was an experiment where you would collect carbon data on the F2 dimension and proton data on the F1 dimension, and it was a slower, less efficient experiment. So we're going to start with these two techniques as our initial starting point for building our toolbox, and we'll see that they're extremely powerful. We're then going to add in Toxie. Toxie is what stands for total correlation, and I'll put that in quotes. It's like a super Cosi that gives cross peaks with all other nuclei in the spin system. I'll show it to you today, but you won't yet have the experience to see where it's useful. We'll bring in some problems later on, but I don't want to bombard you with too much. And HMBC is sort of a long-range HetCore. In fact, that's the version of the experiment that it used to be. And it is basically, these two experiments are a little conceptually more complicated because initially you're going to say, what do I need them for? And it gives you a ton of data. But when you start to encounter specific problems of overlap in the case of the former, and in the case of the latter, fragments that you can't put together, they'll be very helpful. So all of these are correlation techniques. And then we will also throw into the mix of core techniques Nosy and Rosy. These are both Overhauser effect experiments. They both give rise to information on proximity. Nosy is good for molecules that are small and molecules that are very large, but there's a hole right in the middle of medium-sized molecules that don't work well in it. And Rosy ends up working well with medium-sized molecules. All right, let's start with Cosi and HMQC, and let me just show you the general gist of the two experiments. So let's start with Cosi. And imagine for a moment that you have propanol. And so if you think of your H1 NMR spectrum of propanol, you'll probably think of something that looks like this. You'll see a triplet with a 1 to 2 to 1 triplet for the CH2 that's next to the oxygen. You'll see a singlet for the OH, typically, unless you're very free of acid or very free of water. And the singlet is going to correspond to the OH that's going to be exchanging rapidly and not coupling unless you, as I said, are very acid-free. You'll see something that looks kind of sort of like a sextet in a 1 to 5 to 10 to 10 to 1 ratio. I guess that's not the prettiest of sextets. Let me make my outer peaks a little smaller. And then you'll see something that looks like a triplet in a 1 to 2 to 1 ratio. And as I said, you already know correlation. You know that when I see this triplet here downfield, it's telling us that I have and 2 hydrogens. It's telling us that I have a CH2 next to a CH2. And when I see this triplet upfield, I know that I'm having a methyl group with an integral of 3 hydrogens. I'm having a methyl group, and it's next to a CH2. And when I have this sextet here, you know that I'm having 1 methylene group if it's 2 hydrogens. And by being a sextet, I know it's coupling with equal coupling constants to 5 different hydrogens. So for this simple problem, you're very good at reading this. And Cosi is providing exactly this type of information, but in a more systematic fashion. Now, similarly, if I have a carbon NMR spectrum, let's say for the same molecule, I may have something that looks kind of sort of like this, with, let's say, 3 lines in it. And what HMQC is going to do is it's going to correlate the proton signals with the carbon signals. In other words, it's going to say, this proton signal is connected, is coupled with that carbon signal. This proton signal is coupled with this carbon signal. This proton signal isn't coupled with any carbon signals. And this proton signal is coupled with that carbon signal. All right, let me give you a handout that sort of starts us on all of the core correlation techniques, both these two and the Cosi and the Toxie and HetCore. And let me show you schematically what I'm talking about. Ooh. Oh, helps to plug in the machine, doesn't it? That's better. All right. All right, so this is not a real spectrum. This is a sketch of the Cosi spectrum of propanol. And so it's my little pigeon sketch of it. And so a Cosi is going to give us all of our couplings. It's going to give us our J33, in other words, our vicinal coupling, our vicinal couplings, and our J3s and our J2s, in other words, our geminal coupling. Any case you have coupling, you'll get long-range coupling as well. like allylic coupling. In general, if your coupling constants are small, the signals are going to be weaker. So if you have a very small coupling, like an allylic coupling, it may not show up as strongly. Or if you don't go down in that topographical map enough, you may not see it. Later on, we'll talk about some tricks to help bring up those signals. But right now, basically, anything that's coupling is going to give you a peak. Now, remember, I talked about our axes. So this is our F2 axis. This is our F1 axis. And these technically are not part of the spectrum. These are actually one-dimensional spectra added for reference. So you typically, and you'll be doing this, will take a 1D spectrum and you will use it as a projection on the axis so that you see how things line up. Now, in terms of the anatomy of a Cosi spectrum, this is what we call the diagonal. And the diagonal basically is just the spectrum. In other words, it's the methyl peak here, the methylene here, the OH here, and the methylene next to the oxygen. These are the peaks that are interesting. These are called the cross peaks. There are 4 of them here. The cross peaks, if you'll notice, are symmetrical about the axis. And what I always like to do in naming my spectra, and we'll be doing this as a convention in class, is we'll identify all of the peaks in the 1D spectra and we'll letter them starting at the left of the spectrum. So I will call this peak A, this peak B, this peak C, and this peak D. And we'll do the same over here, A, B, C, D. And what the Cosi is telling us is that A, you notice it lines up with A, is crossing with C. And so you see this peak, and so we have this cross peak for A cross C, and you get the same thing over here. And then you have another cross peak here, and that's C crossing with D. And I like to go ahead and basically keep the idea of my peaks and my cross peaks before we assign where those peaks are in the molecule. So of course now we know that in this molecule, this is HB, this is HA, this is HC, and this is HD. And I'll show you as we progress, we'll learn more and more how to systematically extract this from unknown structures. But you can see, for example, that A crosses C, and so that's corresponding to this coupling, this correlation. And we can see that C crosses with D, that's corresponding to this coupling, this correlation. And we can see in this particular simulated spectrum, this particular, I should say, sketch of a spectrum, B, because it's not J-coupled, isn't coupling to anything. If B were a triplet, if it were J-coupling, then we would expect it to give a cross peak with A. And so we'd see a separate peak over here associated with that coupling. All right, so that's our Cosi spectrum. So now let me show you our HMQC spectrum. All right, so this is your HMQC spectrum. Your HMQC spectrum picks up one bond CH coupling. And in picking up one bond CH coupling, of course, now we have no diagonal because we've got on our F1 domain, we've got C13. And on our F2 domain, we've got our proton spectrum. And so there's no diagonal. And what instead we have is a series of cross peaks. And again, if I transcribe the structure of the molecule and I call this HBOCH2A CH2C CH3D for the molecule, now what we're going to do is to correlate these carbon peaks with the proton peaks. And again, I like to very, very, very slavishly label my peaks. So I'm going to go through every time I encounter a spectrum, I'm going to go through, start at the left, go A, B, C, D for each of my peaks. And if I start at the carbon, I'll do 1, 2, 3, and so forth. And one of the reasons I'm so dogmatic about this is because when you get to larger molecules, it's very easy to start to get confused. You'll have one expansion here and one expansion there. If you take the time to do this, it'll always help you keep track of what's going on, particularly when you have many spectra. So okay, so now we have these cross peaks here. 1A, so in other words, I look across 1A, I look across 2C here, and I look across 3D, and nothing's crossed with B. And so I can say, okay, this is C1, this is C2, this is C3. Thoughts or questions at this point?
Is it possible to reverse the spectrum on the bottom?
You mean reverse it and have upfield?
Yeah, so that it looks normal. Like it can
Oh, yeah, it is possible. And in fact, well, let's see, which way is it typically plotted? I think it's typically plotted this way because you could envision picking this up and putting it here. So I think you will always see downfield down here, but I could be wrong. It's of no consequence. Let me put it this way. It's of no consequence whether we go from 0 ppm to high ppm or we go from 0 ppm to high ppm. You will also see, maybe in the textbook, you may see a few HetCore spectra given for some of the compounds. In a HetCore spectrum, the C13 is going to be up here, and the proton will be down here. Other thoughts or questions? All right, I want to throw into the mix. I don't yet expect you to assimilate it because we're throwing out a lot of information. I want to throw yet into the mix the Toxie and HMQC. So the big difference in Toxie and, HMBC, let me again make our little schematic molecule here. Okay, in our little schematic molecule, in a Toxie spectrum, you still get all the cross peaks of the Cosi, but now you get new cross peaks. So we get this cross peak here, and we get the cross peak corresponding to this coupling here. But in the Toxie spectrum, what you also get is a cross peak between these two protons. You don't get a cross peak with this OH if it's exchanging, because if it's exchanging, it's not part of the spin system. But what you get is cross peaks with all other protons in the spin system. And at this point, it's hard for you to see why in heck you'd want that. The Cosi already seems very information rich. But it's very good for dealing with overlap, where your Cosi can't walk you through, and you can break through overlap with the Toxie, where you have peaks on top of each other. And the other thing it's extremely good for is biopolymers, oligosaccharides, nucleic acids, and proteins and peptides, because each residue in a biopolymer typically is one spin system. So I'll give you a quick schematic of the Toxie. We'll have a separate lecture on this later on, but I want to just introduce you to the basic anatomy here. All right, so this is again our sketch of a spectrum, and it looks just like a Cosi. In other words, you have your diagonal. Everything is the same as the Cosi. You have, if I again go and slavishly label our peaks, A, B, C, D, A, B, C, D. You have all the peaks that you would have seen in the Cosi. You have your AC peak. You have your AD peak, your CD peak rather. But now you get this one additional cross peak. So you get A to D. That's unique to the Toxie. And that's that cross peak between these two here.
Do you label the ones at the bottom as well?
You can do that, and you'll find if I do the same thing here, I could call this either C to A or A to C, and I could call this D to A, and I could call this D to C. It's providing no additional information. The only thing that I use this, and it doesn't matter whether you use this half or that half, the thing that I use it for is basically to check if I'm confused, if something's a real peak, if there's a lot of noise or some artifacts, I'll check if it's there in both. Sometimes things will be clearer in one or clearer in the other. That's for homonuclear correlation. Heteronuclear, right. You don't have a diagonal. You don't have this element of symmetry. All right, the last one in our schematic, now we come to our HMBC. And let me again sort of show you in my simple-minded view on the blackboard here. So again, we'll come back to our molecule. HMBC can be like drinking from a fire hose. There's a ton of information there. And what you end up needing to do is use it in a very focused fashion because you'll just drown in peaks. So remember, HMQC was our one-bond CH couplings. In HMBC, we get 2- and 3-bond CH couplings. Not always in a predictable or guaranteed fashion. So in other words, this hydrogen will be coupling with this carbon. This hydrogen will be coupling with this carbon. This hydrogen will also be coupling with this carbon. This hydrogen will be coupling with this carbon. This hydrogen will be coupling with this carbon. This hydrogen will also be coupling with that carbon. So you're getting this tremendous amount, and if the OH is exchanging rapidly, it won't be coupling with any of them. And again, right now, it's too overwhelming for you at this point to just throw all these spectra at you and say use them. So what I'm going to put it is just like I say, this is particularly, Toxie is particularly good for overlap in biopolymers. What I'm going to do is say that HMBC is particularly useful for what I'll call putting the pieces together. And you know how on the homework I'm telling you to write down fragments, things that you know. I know this molecule has an ethyl group. I know this molecule has an isolated methyl group. When you're getting to that point and you have these fragments and you're saying, now how in heck do I systematically put them together? This is where HMBC shines, where you say, oh, now I can see that this fragment is somehow connected to that fragment, where you have these isolated spin systems and you're trying to put them together. So I'll give you the schematic of an HMBC right now.
So there's no single bond coupling?
Ah, great question, James. Yes. You will sometimes see single bond coupling. And your textbook actually removed it from a few of their problems, and I put it back in. I basically took out. Well, the reason is, what good is it to have spectra in a textbook that are doctored when you then encounter real spectra? To put it another way, you encounter them in your research or the exam, which may be on people's mind more, and it looks different, and you're like, what the hell's going on? So you can see those, and we will get used to that. We will see that.
But they're rare?
They are, yeah, rare, and usually in the case of strong peaks. And you will know because I will refer to them as, you will see them as these, hey, it's Halloween, vampire bites around the peak. They are, you will see the J1CH splitting them. All right, so if we again go back to our system here, so you notice now we're getting this very rich piece of information here. So for example, if this is our molecule OHB, CH, 2A, CH, 2C, CH, 3D, and we already know these are carbons 1, 2, and 3. So we'll just look at two of these. So this cross peak here of 1 to D, that's telling us that we're seeing, and again, this is just my sketch, that's showing us that we're seeing this long-range heteronuclear correlation. This cross peak here of 2, that's my scrawl of a 2, this cross peak here of 2 to D is telling us that now we are seeing this correlation over here. And you will see how to use this very, very information-rich system in the future. Yeah, and it's not so much how far. Remember how I said that J2CH and J3CH are typically 0 to 20, and they're going to depend on higher 0 to 10. They're going to depend on hybridization. They will have different intensities based on the J value. If your J value is very, very small, you won't pick it out up no matter what. If you've got a J of like 1 Hertz, good luck finding that coupling. And this is the killer on HMBC, is that you can't tell your J2CHs from your J3CHs. So you get this information, but there are always these question marks. Are they direct, are they neighbors, or are they nearest neighbors, or are they neighbors one down the road? But don't worry about this right now. We're going to spend a week or two not using HMBC. What I do want to start us out now is on an example with HMQC and Cosi and show you how beautifully they work together and show you how I solve a simple problem. And this is a problem from not this week's homework, but next week's homework. So it'll be sort of a demo problem for you. And if anyone didn't get one, there's enough to go around. Now, the other thing I would like to give you is a tool that's useful, particularly when you get more crowded spectra, and that's these grids. They're very useful in helping you line things up. They're yours to keep. And you can print more on transparency film, or if your lab mates are envious of you and steal them, you can go ahead and get them. All right, now, all right, what the heck? Okay. So I want to whip through this kind of sort of quickly. So, okay. This is a spectrum, and we have A mass spectrum, we have an IR spectrum. Now, the reason I've been pushing on you, write fragments, write pieces of information, is it helps you organize your thoughts. And it helps me if I go ahead and you get an answer wrong, it helps me figure out what your thinking was, because often there's good thinking in a wrong answer. All right, so I look at this spectrum, I see a carbonyl, I see something at 1743, I work out the formula from the mass, it's C7H14. O2 works out for the mass. There's 1 degree of unsaturation. And it sure looks like it's an ester. 1743 is about the right position for an ester. Here there happens, it's a small molecule, very small molecule. I happen to see the CO single bond stretch. If I look in the proton NMR spectrum, I see some downfield peaks that look like it's consistent with an ester. So take it as a given right now that it's an ester. I go ahead and I look at my peaks, and again, I really, really, really like to get in the habit of labeling them and just walking across the spectrum, A, B, C, D, E, F, G. It's a little confusing here. If I look closely, it looks like I see a doublet. Can you see the pattern of the doublet on top of a triplet? You see the 1 to 2 to 1 triplet. So it looks like I have G is probably a doublet, and H, so that's probably G, and that's probably H right over here. Now, you really, really, really want to be diligent about putting a ruler, measuring the height of your integrals. I like to be good. I like to take this height, 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 everything I'm sure of, divide by the number of protons, and get the most accurate height per proton possible. This one is pretty obvious to follow by inspection. If I'm really feeling lazy, I could always just even use my grid as some sort of Uber ruler, and I say, oh, 1.7, 1.7, 5 point, looks like about 5.3, 5.4, yeah, 5.4, 1.7, or 1.8. I guess if I want to be good about it, I will even try to line up my grid a little bit better. Yeah, about 1.7, 1.7, 1.7, about 2. About, let's see, about 10.6. And if I work this out, I'm getting about 1.7 per hydrogen, say about 1.7 per hydrogen. This ruler, by the way, is graduated in tenths of an inch, is the small tick marks on there in case you're wondering. All right, so I can very quickly go through and say 1 hydrogen, 1 hydrogen, 3 hydrogens, 1 hydrogen, 1 hydrogen, 1 hydrogen, and this looks like 3 and 3. It looks like it's 6 hydrogens. Similarly, I like to look at the carbon NMR spectrum, and if I have a depth spectrum, I'm very happy. And again, I'll go and number my peaks: 1, 2, 3, 4, 5, 6, 7. And I look at my peaks and I say, oh, it looks like 1 is a quat carbon, 2 looks like a methylene. I may have to make judgment calls if my depth isn't completely clean. 3 is a CH, 4 is a CH2, and 5 through 7 are CH3s. Now, with these data alone, I'm going to have, this is at the harder end of a molecule to solve with just 1D data. It's not that you can't. You could easily puzzle out the structure, but I want to show us how 2D data is going to help us. Usually at this point, I sort of jot some ideas down as fragments. I see I have a methyl group at 2. I don't know, maybe a methyl group at 2 might be indicative of CH3. Carbonyl might be something. I think I have, it looks like I have 2 methyl groups here. One of them's a triplet. One of them's a doublet. So I probably have, if I'm just tallying up fragments, I probably have a CH3, CH2 fragment, and I probably have another CH3, CH fragment. And honestly, if you puzzled around now, you could probably put the structure together. But I want to show you this way of putting the structure together that we're going to do here using HMQC and Cosi in a systematic fashion. All right, I actually like to start with my HMQC spectrum. And the reason I do is that's going to help me. First of all, it's going to avoid having me waste a lot of time getting stuck on geminal couplings. And it's going to give me a very systematic way of naming things. And again, I'm going to be very slavish. A, B, C, D, E, F, G, H, E, F, G, H. And you notice we've left out the carbonyl. We left out the carbonyl at about 100. Oh, that was another thing that clued me into to an ester. The carbonyl was at what, 170-something ppm? Typical ester, so it's not a methyl ketone. It's not an aldehyde, right? A methyl ketone I'd expect at like 205 to 220. An aldehyde I'd expect at like 190 or 200. So I am pretty darn sure this is an ester. Anyway, but we don't need, in HMQC, it's not going to correlate anything because it's a quad carbon, it's not coupled. So I start my numbering 2, 3, 4. What am I doing here? Whoops. Hard staring in the light. 5, 6, 7. And now I just look at my cross peaks. And so 2 is crossing with A and B. 3 is crossing with D. 4 is crossing with E and F. Every time I get one of these carbons crossing with 2 methylenes, I know it's a diastereotopic methylene. 6 is crossing with, now this is where it's hard to see. And if you have trouble, particularly in a crowded spectrum, just slap a grid on it. And you can see one cross peak lines up kind of centered with H. The other cross peak lines up with G. They've included an expansion here. I believe they have actually forged their data here. I think this cross peak actually should be spread out, and they were trying to make it easy for students by showing it just under here. But again, what good is that going to do for you when you encounter your own real data and you say, oh, it doesn't look like it looked in the problem? So here I look and I see, oh yeah, you see how nicely you can see with the grid lines, this lines up with G, this lines up with H. So okay, so we get 6G and 7H. And now I'm going to be this is going to become my Rosetta Stone for the problem. I'm just writing all of my numbers here right over the letters. 2A and 2B, 5C, 3D, 4E, 4F, and 6G, and 7H. All right, here's where all of this work pays off. Now we go to the Cosi spectrum. And what I do, again, I'm very, very, very mechanical about this. I go ahead and I transcribe from my other axis 2A, 2B, 5C, 3D, 4E, 4F, 6G, 7H. And I do, if I had another axis up here, I would do the same. They only gave us one edge projection. That's not going to matter. All right, we're now all set to put this molecule together. All right, so I go through now, I identify my diagonal. I draw a line through my diagonal so I don't get confused. Ruler is better than the side of my grid, but if the grid is what I have on me, then I use the grid. David always comes prepared. He has his ruler. All right. Now we're ready to look at our cross peaks. 2A crossing with 2B. That's just, I'm taking the 2A and the 2B diagonal. They're crossing with each other. Normally I go up and over, but here, because they're all on this side, I go over and over. So OK, tell us something we don't know, right? That's our C2, HA, HB. The only thing I really do know at this point, that's the carbon at 70 parts per million. So I know that that carbon probably is connected to an oxygen. I think I have an ester in here. All right, here's where we start to get some new information. Because 2A and 2B each cross with 3D. See, I can go up and over. So that's useful. 2A with 3D and 2B with 3D. OK, that's useful, because now I know I have C3HD, and it's connecting. And I'm starting to put this thing together in a systematic fashion. And I'm just going to continue to read my spectrum. So we go over here, and we say, oh, here we get 3D cross 4E and 3D cross 4F. And you say, oh, OK, that's useful. I have this methylene C4 with E and F connected. It's got to connect up. C4, HE, HF. And I'm building up this chain that's harder to put together than a usual coupling where we can just read off and see what's coupled with what. And you say, hey, this is useful. And I look up here, and I say, OK, I've got this cross peak. Maybe I need to slap a grid on it to help see how things line up. And I look at my grid, and I say, it looks like that aligns with 6G. And so now I say, OK, so I have 3D lining up also crossing with 6G. OK, so 3D also has to cross with C6, H3G. And now I have almost the entire chain built up. All right, I have this cross peak here. Does that tell me anything useful? What's that cross peak? So I go over. Normally I'd go over and up, but it's 4E cross 4F. Well, that's fine and dandy, but it isn't telling me anything useful. 4E cross 4F, that's just the diastereotopic one. But now I come to the last ones, and I get 4E with 7H. You notice this one's lining up with the full edge. So 4E to 7H. And this one's 4F to 7H. And that gives me the last of my chain, C7H3H. All I have left now is I have this isolated methyl, C5H3C, right? He's not correlating with anything here. If I had an HMBC, I could put them in systematically. I have one carbon left. That's C1, which is part of a carbonyl. That was in my other one. And you can see how it comes together now. We had 2 valences on the carbonyl that needed to be filled. We had a valence on C5H3C that needed to be filled. We had a valence on the oxygen that needed to be filled. The only way to put the molecule together was to connect that valence from C5H3C to C1 and the other valence on C1 to the valence on oxygen. And bingo, you have the whole structure systematically worked out. Obviously, it's not as easy the first time around as I make it look here. But the same strategy, we'll start with a simple problem set next week. The same strategy of going ahead and working the HMQC and then working the Cosi is going to take you very far.